Next, let's cut the shoulder on the end of the workpiece. If we look at the part drawing, we can see the dimensions for the shoulder are approximately 1.25 inches in diameter and 1 inch in length. Looking at the part, we can't just cut this in 1 or 2 passes because the depth of cut, meaning the radial distance that the cutting tool is engaged in the rotating workpiece, the depth of cut would be so large if we tried to do it in 1 pass that the cutting forces would also be proportionally high, and they would cause excessive deflection of the cutting tool and vibration between the workpiece and the cutting tool. Okay, so on any machine tool, there's a practical limitation to how deep you can cut per pass that's inherent in the structural rigidity or stiffness of the machine tool. On a lathe of this size or this class, the limit when cutting a softer metal like aluminum is going to be 0.1 inches on the radius, or 0.1 inch depth of cut, or 100,000ths of an inch. If we move the cutting tool in 0.1 inches on the radius, then the actual diameter of the workpiece will be reduced by twice that amount, or 0.2 inches. Our digital readout, it reads out on the diameter because it makes it a little easier to compare what it shows to measurements made with calipers, since we're always measuring the diameter of cylinders using calipers. Okay, so the DRO reads out on diameter, okay, but our tool is always moving on the radius. So what that means is to adhere to this rule, or this maximum limit of 0.1 inch maximum depth of cut, we are going to reduce the diameter by 0.2 inches each time we make a pass along this shoulder length. Let's begin, and then we'll talk about a few more details. Okay, I'm going to go through the 3-step check. I'll put the machine in neutral. I'll turn the workpiece through 1 revolution, make sure that there's clearance between the cutting tool and the workpiece. I'll put the machine back in high range, and I'll make sure I turn it on in the forward direction. I'll check my spindle speed. We want to be somewhere around 400 RPM, just for the sake of making the audio a little easier for you to hear. Okay. And now we're ready to begin. I'm going to move the tool in the Z-axis close to the front of my workpiece, which would be Z0. I'm going to go to about Z.1. And now I'm going to move the X-axis. I'm going to move the tool in towards the part in the X-axis until I reach our 0 that we set previously. And I'm going to go in 0.2 inches on the diameter. And again, this is equivalent to a 0.1 inch depth of cut, which is the maximum we can take on this size machine. Okay, so the important point to take away, 1 is that there's a limit, and 2, that there's a roughing cut, which is what we're about to do, meaning we want to remove a lot of material quickly because time is money. However, as we get closer to the final dimension, or closer to our final tolerances, we're going to slow down, or we're going to lessen our depth of cut, and instead of taking the maximum or taking a roughing cut, we're going to take a finish cut. And a finish cut is typically defined as anything that has a depth of cut less than about 20,000ths of an inch. Okay, so we're going to get to that. Let's start by getting close to our 1.25 inch dimension. Okay, so I'm going to use use cutting oil, since we'll be removing a lot of material now. I'll put a little oil on the tip of the cutting tool. Use my right hand to make sure my body doesn't come close to the dangerously rotating chuck jaws. What I like to do is move out here in space before I make my first cut, and I want to ensure that I have the automatic feed controls set properly on the apron. So first I want to check my direction. I am engaging the longitudinal feed, the Z-axis feed. That's what I want. And if I engage it, I can see that it is moving the correct direction. It's moving from the tailstock towards the headstock. Okay, so everything is set up properly. I'll come back close to the front of my workpiece. And actually, I'm going to gently engage the workpiece just to make sure that I see a chip, make sure everything looks okay. And now I'm going to use the automatic feed. As I engage it, it'll begin cutting the workpiece. We'll see the chips begin breaking up into small pieces. And I'm going to pay attention to the digital readout. Anytime that I want to stop and slow things down and just double check what I'm doing, all I do is what I just demonstrated. I just turn the automatic feed off, and then I can very calmly look at my digital readout. If I need to check something, I can turn the machine off and check that. I can compare it to my drawing. Okay, so you can turn the automatic feed on and off as frequently as you desire. I said that the length of the shoulder on our workpiece is 0.1 inches. Okay, but I don't just want to feed right up to 0.1 inches because I can't turn the machine off instantaneously. So I'm going to turn the automatic feed off when I get close and finish up the last little bit by hand. So I might automatically feed to 0.9 or 0.95 inches. I'll turn the automatic feed off, and then I'll finish the last little bit by hand because I have a lot better control over not passing my 1-inch target that way. Okay, so I'm going to engage the automatic feed again, watching the digital readout, 0.6, 0.7, 0.9, 0.95, somewhere around there. I'm going to turn the automatic feed off, and now I'm going to use the Z-axis hand wheel to controllably move the cutting tool in to about 0.9, I'm at 0.98, 0.99 inches. Okay, I like to leave 10 or 20 thousandths of material for that last pass, for that finish pass that I alluded to previously. Okay, as we do multiple passes, we're going to see a little staircase develop on the part. So I'm going to leave a little material for the very last pass so that we can clean all those individual steps up and make the shoulder very smooth and geometrically correct. So I'm going to stop there, and now manually I'm going to reverse the direction. I'm going to move the tool towards the tailstock, just like a steering wheel on my car, back to the front of the part, and now I'm going to repeat what you just saw me do. I'm going to move in another 0.1 inches depth of cut, which is 0.2 inches on the DRO. So now I will be somewhere around 0.4 total on my X readout on my DRO. Okay. I'm going to reapply oil. I'll come back up gently to my part, re-engage, and then use my automatic feed just like I did on the last pass. Okay, I'm watching my DRO, I'm watching my cutting zone. Again, if I want to check something, I can stop the automatic feed. The tool's just rubbing right there. You can see it looks like it's cutting a little ribbon. It's actually pretty cool because we're cutting a lot of material off each pass, so the tool is deflecting. So the instant that I stop the automatic feed, you're actually seeing the tool deflection become less. So basically it's returning to its normal position, which is why it's still cutting a very small amount of material as the tool essentially springs back to its normal state, normal unloaded state. Okay, so that's why the chips eventually stop. So I'll continue. I'm at 0.6 inches in the Z, and I'm going to feed again until I get to about 0.95 inches, and then I'll stop, and I'll finish up the last little bit by hand. Again, I'm going to feed into about 0.99 inches, 0.98, 99, anywhere in there. And then I'll feed back across my part. I'm going to do this one more time. So I'll feed in another 0.2 inches on the diameter, which is our 100 thousandths maximum depth of cut when cutting aluminum. Okay, close to it. A little bit of oil. And repeating the process a third time. Half inch, 3/4, 0.9, and I'll finish up the last little bit by hand. Again to about 0.99 inches. Somewhere around there. Okay. Then I'll feed back off my part. I'm going to go a little bit farther this time, out in space, and then I'll reach over and I'll turn the machine off. I'll wipe the part off with a rag, wipe the cutting tool off. I want to make an important point here for safety. Anytime we use a machine tool to cut a workpiece, whether it's a bandsaw or a lathe or a milling machine, really any type of machine, whenever we make a cut on a workpiece, the resulting edges are going to be extremely sharp. Okay, they're like little tiny serrated knives. So you never want to quickly run your finger over them because they will definitely cut you. So always use a rag to wipe off the workpiece, at least until you've deburred it with a file, like we're going to talk about soon, or cut a chamfer onto the edges. Again, like we will demonstrate in a few minutes on this part. Okay. What I want to do now is I want to just stop and check where we are as far as what our destination is. We wanted to reduce this diameter to 1.25 inches. Okay. So if we start off at 2 inches, which is what I think we measured previously. Yep, measured 2 inches on the diameter of the rough stock. If we start off at 2 inches, we essentially need to remove 0.75 or 750 thousandths off the diameter of the workpiece to get to our 1.25 inch dimension. Okay, we've removed 0.6 inches so far. So what I want to do is just make a quick check, or make a quick measurement with the calipers to check that I haven't made a mistake and that the DRO is giving us a reliable reading. So I'm going to grab my calipers. I have them over here out of the way so that no chips could get to them. I'm opening them. I'm going to check the zero. The zero looks good. I open them and I'm going to make a measurement. Okay. My measurement is 1.4, looks like 1.4, 0, so we are exactly where our DRO told us that we should be, maybe within a 1,000th of an inch. Okay, so the reason that I'm doing this, like I said, I always like to trust but verify. I've worked with these machines a long time. I've used a lot of digital readouts. They have proven themselves to be very reliable. I always like to just check early in the session to make sure. And actually, if it's an important point, an important part, I will check on each feature just to make sure that I don't waste the material by doing something that a second set of measurements would have caught. So in this case, the calipers are verifying that the DRO is very trustworthy, so we can continue. You can see that from my math, we have about 0.150, about 150 thousandths left to take off the part. Okay. Earlier, I told you that a finish pass is about 20 thousandths of an inch. So what I want to do, if we have to cut 0.150 to get to the nominal dimension, meaning the midpoint of our tolerance range, if we have to cut off 150 thou, I want to leave 20 thousandths, at least 20 thousandths to do one finish pass. If it's an important feature or if it's a really tight tolerance, I will leave enough to do multiple finish passes. Okay. On this diameter, it's you've heard me say 1.25 several times because that's exactly how it's dimensioned on the drawing. 2 decimal places results in a tolerance, an associated tolerance of plus or minus 20 thousandths of an inch. Okay. So what I want to do, I'm repeating myself now. We need to cut off a total of 150 thousandths. I'm going to cut off 130 thousandths on my last roughing pass. I'll make one final measurement and then I'll do a finish pass to bring the part feature into final size. Okay, so I'm going to increment my x-axis into, let's say, 730 thousandths. $730. I could go a little bit more than that. It doesn't matter, but you understand what I'm saying. I want to leave a little bit of material to do a finish pass at the end. So let's do 735. Okay, about 735 thousandths. I'll reapply the oil. I stopped the machine in a safe place, so I don't have to do my 3-step check this time, but I will because I like to be safe. So I'll spin it one time, everything looks good. I'll put it back in high range, and then I'll make sure that I'm turning the machine on in the forward direction. Okay, I'll come back up to my part, 2 hands on my Z-axis hand wheel, gently engage the part. I can see the chips coming off, it means I'm spinning the right direction. That's why I always like to touch off by hand. even when using the automatic feed. And now I can continue by engaging the automatic feed in the longitudinal or the z-axis direction. Half an inch, about 3/4 of an inch, and I will stop around 0.95 inches again and finish up the last little bit by hand, going to 0.99 or somewhere around there. I'm going to back off the part, turn the machine off, wait for it to come to a complete stop. I'll grab my calipers, double check my zero. Looks good. And I'm going to make a final measurement here before we make our last cut. Okay? So in this case, I am reading 1.265. 1.265. Okay? Our final dimension is 1.250. Okay? So I'm exactly 15 thousandths large, and that's what my DRO said. So again, I'm getting very good agreeability or reproducibility between the calipers and the DRO. So my last cut, I'm just going to go right into 750 thousandths because that would be the middle of my tolerance band. Okay, a little bit of oil. Don't need very much because it's a finish pass. Okay, but before I make this cut, there's an important point that I want to discuss. Right now, if our part measures trying to read the calipers upside down, 1.265, and our tolerance, our dimension is 1.25 plus or minus 20 thousandths, technically, right now, that feature diameter, it's within tolerance. Okay, so if someone else was making this part for me and I was paying them, they could stop. They've met my legal contract. They met the design intent of my drawing because they are within that tolerance range. Okay, so you're either in or you're out. It's binary. They don't get points for trying to get closer to nominal size. If we're making our own parts, usually because of just the sense of pride that we like to take in our work, we might put more time into to trying to get right in the middle of the tolerance range. Okay, but when it comes to tolerances on a feature, on a part drawing, again, it's binary. As long as they're within the range, then they can stop. They don't need to do any more work. So if I require this to be closer than plus or minus 20 thousandths, as the engineer, as the design engineer, I have to specify that on this feature via the tolerance. Okay, and the same thing with the surface finish. If I need to have a particular surface finish, then I have to note that on the drawing as well. Okay, but I just want to use this as a good illustration. Okay, we do not need to make another cut on this part. It is within size. For surface finish, it just says finish all surfaces on this part because it's a demonstration part. We'll learn later that it's rare that we finish all the surfaces. We want to show you as much capability as possible on the lathes and the mills. So we're going to finish everything because we're learning what the machines can do. But we'll learn later, okay, if a surface isn't critical for function, then tell them don't touch it, don't finish it, don't add time and cost to my part features unless I need them for to fulfill my functional requirements. Okay, so back to this. I'm going to make this last cut, again, just because I'm trying to illustrate roughing passes versus finish passes, and a technique that if you follow it, meaning do your roughing passes first and leave 1 or 2 finish passes, if you follow that, regardless of what materials you find yourselves cutting, you'll be able to achieve very tight tolerances on precision machinery like this lathe. Okay, so I'm going to check. We have clearance between the part and the cutting tool. We're in high range. I will turn the machine on forward, come back up to the front of my part, gently touch off. There we are, and engage my automatic feed. So now we can see a very fine chip being produced because we're not cutting much off at all. We're cutting 7.5 thousandths off on the radius of this part. So I'm going to watch my digital readout. When I get to 0.95, I'm going to stop. This time, I'm going to feed all the way in. Instead of stopping at 0.99 inches in the Z direction, I'm going to keep going until I get all the way to 1 inch. And once I do, I'm going to change the automatic feed to the x-axis. So instead of the longitudinal, I'm going to change it to the cross feed, or the x-axis, engage it, and then have the machine, the lathe, automatically feed my tool outward, cleaning up those previous steps that I made as I performed multiple depths of cut on the face of this shoulder. Okay, so I engage the automatic feed. It begins retracting the tool towards me. You can see the chips being produced. It's smoothing that surface, making it very flat with respect to the axis of the cylinder. We're finished, we're all the way out. I turn the automatic feed off. I turn the lathe off. I can move the tool out of my way. And the last step, I always like to measure, just to make sure that I'm confident that our features are within tolerance. So the calipers are zeroed. On this, I get exactly 1.250. So that's exactly on size for diameter. The length we said was 1 inch. If I use the depth portion of the calipers from our previous video, I can check, I can measure, quickly measure the length of this shoulder. Let me see if I can do this and get a good measurement without bumping the camera. Okay, and on this, same thing. Here I get exactly 1.000. Again, it's showing that the digital readouts are deadly accurate, actually, on these machines. So very trustworthy, very reliable. I just want to make sure that I hit everything that was important. We talked about roughing versus finish passes. Again, the cutoff is about 20 thousandths of an inch. A depth of cut less than 20 thousandths is going to be considered a finish pass. In aluminum, I said there's a or for any material, there's a maximum depth of cut. For aluminum on this machine, it's 100 thousandths. Depth of cut is always on the radius. Okay, if the tool moves in 100 thousandths to make a maximum depth of cut, then the diameter of the workpiece will be reduced by twice that, which is why you kept seeing 0.2 inch increments on the DRO. You saw me using the calipers occasionally just for a reality check, just to double check where I was before I reached the final feature size. We talked about tolerances and the fact that they're binary. You're either in the tolerance or you're not. And if somebody's in, then we have to pay them. If they do that for all of our features, they legally met the binding contract inherent in our part drawing. The next step for this part would be to cut the 2 chamfers on the leading edges. So let's go ahead and do that. I'm going to remove this turning and facing tool from the tool post. So I push the handle away from me, and I can easily take the tool, the cutting tool, off the tool post. I'll wipe it off for now and just set it to the side. I'm going to grab a tool that is a chamfering tool. You'll see it on the tailstock camera in a minute. But essentially, it's the same type of tool, just oriented so that the included angle, the 90-degree included angle of the cutting tool is perfectly aligned with the x-axis, which will produce exactly a 45-degree chamfer if we bring it into contact with our workpiece. Okay? The easiest way to demonstrate is just to show you. Looking at the part drawing, it calls out 2 chamfers on the front 2 edges of our parts. They're identical in geometry, and they're 30 thousandths by 30 thousandths by 45 degrees. Okay? So to cut a chamfer, I'm going to turn the machine on using a 3-step check. Check for clearance, put it in high range, turn it on and forward. To cut a chamfer, I'm going to bring this long 45-degree corner of my cutting edge gently into contact with the rotating edge of the workpiece using the X or the Z axis, it doesn't matter. So I'm going to feed this in slowly until I just see a chip being produced. There we go, there's a chip. I'm going to zero my Z-axis, and now I'm going to use the Z-axis hand wheel to move the cutting tool 30 thousandths towards the part, giving me the proper geometry. The reason I'm using the Z-axis hand wheel is because it's large. It's just like the steering wheel on your car. They purposely make them large so you have a lot of control when using them. Same thing with the Z-axis hand wheel. Okay, I've got a lot of control. I can watch my digital readout, and I'm going to feed all the way to 30 thousandths. So 10 thousandths, 20 thousandths, 30 thousandths, and then I'll move away from the part. I'm going to move over and repeat the same process on the second edge. So I'll gently come into contact right there. I'm going to zero my z-axis, and then use my z-axis hand wheel. I'm going to gently move over 30 thousandths, the size of my chamfer. Okay, I'm going to move away from the part now. I'm going to turn the lathe off and wait for it to stop. And I'm going to grab my calipers. And just like on the last feature, I always want to verify what the DRO is telling me. So I'm going to use the calipers to measure the length of my chamfer. In this case, a quick measurement tells me that chamfer is about 31 thousandths. Okay, so that was just quick by eye. So again, I'm just verifying that I didn't make a gross error somehow in touching off, or maybe I forgot, maybe I didn't push hard enough when I zeroed the DRO, or something strange like that. The guys like to always verify. Now we have the shoulder machined. We have the outside diameter of the large portion of the wheel hub machined. We have the two chamfers that break the sharp edges, and also if this part was going to slide inside another one, those chamfers could be functional. On this part, we're just including them to show you some variety, different types of tools that are commonly used on the lathe. Okay. The next feature that we can do on the lathe is the center hole that goes through this part. However, if we're going to drill all the way through, since we have to cut the hub, we have to cut the wheel hub off of the stock we're using for clamping anyway. If we have to drill all the way through, it makes sense to cut it off first. That way, when we're doing the drilling, we can just drill into air. We can drill all the way through the part and just exit the part into air, so we don't need to keep track of how deep we're going with any of the drilling tools. So that's the sequence that we want to do it in. Excuse me. To prepare to cut it off, okay, we're going to use a ruler and a Sharpie, and to note our cut line. Our part overall should be 1.5 inches long. We're going to cut this off on the bandsaw because the bandsaw is a very quick way for cutting materials to length. The bandsaw is not nearly as accurate as the lathe, so because of that, I'm going to leave some extra material. I'm going to leave about an extra 1/8 of an inch. So instead of cutting it off at 1.5 inches, I'm going to put a mark at about 1 5/8. And that's my target cut line for when we go over to the bandsaw and cut the wheel hub off the stock that we're using to clamp it in the lathe for this first operation. Okay, so I'm going to stop here, and we will progress to the bandsaw.